All right, so let's get started here. So the announcements are all the same. Pretty much, you have a homework due tonight. And this is loud. You've got online homework due on Wednesday night. And then the last online homework before the test is next Monday. And then we'll have the test next Thursday, 6 p.m. to 7:30 p.m. in this room. And then I'll also post the review sheet and all that sometime this week. All right, so let's get into the notes. We're looking at R value, stuff like this. We're on page 81. All right, so the correlation coefficient, is it resistant to outliers? Well, let's just look at a couple of examples here and see what would happen with and without the outlier. So on this first example, everything's kind of like just a random little cluster down there. Just a bunch of little dots. But then there's one outlier way out here. So we've got R is equal to, it's really close to 0 without the outlier. Oh, yeah. There we go. That good? Awesome. So yeah, without the outlier, it's very close to 0. But then with the outlier, it's much closer to 1. 0.90. So the outlier has a huge effect on this R value. And then here, it can go the other way around too. So you could have a really strong correlation. So R equals 1 without the outlier. Oh, how do I get that? So we would need to type these into, well, you could work them out by hand like with the table that we did before. But you're just going to have to trust me now because we don't have the numbers with each of them. You could type them, if you have the data set, you could type them into your calculator, and then your calculator could give it to you as well. Yeah. But for now, I want you to make the connection with what it looks like with which R values I'm giving you. So you should be able to look at a scatterplot and say, okay, is it have a high positive R value or like a low negative R value? It's going to be close to +1 or close to -1. Because remember, we're not going to see any R values of 3 or 3,000 or -3 or -3,000 because of the formula. It won't give us numbers that large. So, right. And then without the outlier, so this one was fabricated so that it would, or with the outlier, so that would be 0, R equals 0. So the outlier changed from changed the R value from a strong value to a very no correlation there. So, all right. Any questions with this? So the correlation is, coefficient is very sensitive to outliers. But you may not know which way. So the correlation coefficient is very useful when it comes to the linear model, because next chapter we'll be talking about linear regression. And with that, it'll be useful to know what is the R value, how much can we trust these this model, the predictions based off of this model. Okay, so you also, here's a little tip here. You want to always look at the scatter plot, because we want to make sure that there's actually a linear relationship. So here, this one, this isn't linear. This one's pretty much linear, but then there's this outlier that may affect it. And then all of these, they've got lots of weird things going on. But then all of them have one thing in common, and that is the R value. So the R value for all of these is 0.70. So that is the same for all 9 scatter plots. Right there. All right, so these have very different patterns in the scatter plots. So if you just looked at the R value, you could be like, well, that's a moderately strong correlation right here. But then you look at some of these and it's like, well, no, this doesn't even look like a line. This one looks like a weird banjo. Like a banjo right there. This one looks like a swoosh. And here, for some reason, all of the points are in the bottom right. They just don't even go up to the top left of the space here of the graph. So yeah, very different things going on there. All right, a caution here. So when it comes to causation, so just because you can make a really great prediction or you've got a really strong R value, really close to 1 or -1, you can have some issues when you're saying that the one variable is causing the other variable, because maybe there's something else going on here. So with this scatter plot, we've got number of TVs per 1,000 people versus life expectancy in years. So then we see that there's a moderately strong positive curved relationship between the two variables. Kind of goes like this. We wouldn't want to give, I mean, it wouldn't be entirely appropriate to give an R value here because it's not a linear relationship. The points aren't lining up that well. But as far as if more televisions cause life expectancy to increase, you would think that, well, maybe that's kind of a bogus claim. Like, how would televisions actually cause this? Like, do they make you healthier, or do they make you? I guess maybe they can make you happier, but I don't think that's going to cause life expectancy to go up so high. So another explanation would be higher country wealth could be the cause of more televisions per 1,000 people. And higher life expectancies. So there's this third variable that's affecting both of these variables and is possibly the cause. So this is just an example to show that correlation does not mean causation. Another nice catchy little line would be, so no cause in means no cause out. So that's another thing you could think about. How that would make sense is that you're not affecting anything when you're gathering this data. It's just, you're just observing it. It's an observational study. But with experiments, you're actually affecting. So you're causing something to happen. You're splitting people into groups, and you're actually causing a change there. And then you would expect to find some kind of a cause out of that experiment. Okay. So we're not like into the experiment chapter just yet, but I'm trying to prep you, trying to get you ready for the future. All right, so this is called a lurking variable because it's in the background. It's not explicitly stated in your study or in your questioning. So bottom line, two variables may be strongly associated, but they may still not have a cause and effect relationship. So you gotta watch out for that word cause. That's another bottom line. So like if a question is asking you if something is causing something else, then make sure it's an experiment, a well-designed experiment. So here's another causation example. So if we have, okay, so on the left here, we've got Nobel laureates per 10 million of the population. And then on the x-axis, we've got chocolate consumption, kilograms per year per capita. So how much chocolate do you eat in a year? All right, so here we've got US, it's about here in the middle of the pack. But then we've got places like Germany that eat a lot more chocolate. We've got a similar number of laureates. But then Switzerland, I mean, they eat a lot of chocolate and they've got tons of Nobel laureates. And you can look at this and you can see, okay, so we've got R of 0.791. So that's a moderately strong R value. So these are somewhat linear. So so there is a relationship here, but then it's not a causation. There may be some kind of a third lurking variable. That's the point of this example. So chocolate consumption may not cause Nobel laureates. All right, another example would be there's a highway speed limit in 1974. So the speed limit was decreased. And then when that happened, the number of traffic fatalities also decreased. So you could maybe say, oh, well, that seems like, oh, of course, you're going slower, it'll be safer. But then there was another thing that may be the actual cause would be that the gas prices were higher So during that time period, the gas prices were higher, and this may mean that fewer people were on the roads. And so fewer people driving means fewer people dying from driving. All right. That may actually be it. So even if it can be somewhat seductive, you may think, oh well, of course this makes sense. You know, going slower, it's safer. But don't fall for it. It really needs to be some kind of a well-designed experiment to go for that cause word right there, to say that there's a cause. So yeah, gas price was the lurking variable here. And here's an interesting example. So we've got autism and organic food sales. There is a very strong R value between the two of these. So you wouldn't think that one causes the other, though. It's just kind of a coincidence. It's kind of a strange coincidence. So yeah, the R value is actually 0.9971 is what that is, which is super high. All right. Lurking variable. It could be increase of population, or it could be some kind of overall cultural trend. I'm not saying that. Yeah, I don't know. Maybe it's just autism awareness kind of goes along with the trend of healthy eating. I don't know. We would have to do an experiment, I think, to get to the bottom of that. Yeah. All right, time plots. So pretty much time plots are, they just have the x-axis is time, and then you connect the dots with lines. So let's say an example would be like these two right here. So we've got the number of Canadian lynx trappings over 114 years. And then we've got, and this is in Canada, and then we've got a plot of quarterly every 3 months gross business income for the state of Washington. All right, so the things you want to look for is if there's any, is there a general overall trend up or down, cyclical patterns. You want to look for if the variability is constant or if it increases or decreases. You could look for anything that's unusual or interesting, so like a sudden change or something like this or that. And in these ones, you can see, well, let's just do one at a time here. So with this one, you can see that it goes up and down, up and down, up and down a lot. But you see that it's about every 10 years or so that you get this peak. Every 10 years or so. And then you also see that there's these really huge peaks every 40 years or so. So that could be something you would write down, some kind of patterns that you see. And then in the Washington one, you see that it goes, every year there's a cycle. So it goes up, down, up, down, down. So it's every fourth quarter is the peak. And then there's also an overall trend upwards, increasing. So those are two things that are going on. You didn't see that overall increase with the lynx trapping. It was just somewhat flat. So yeah, let's write some of this stuff down. So that's the patterns that I list off that you would look for up on the top. And then what do you see in the links trapping plots? Let's try to write this carefully down. So this one, there's a clear cyclical, so it's like a cyclical pattern in the number of links trappings. Which peaks every 9 to 10 years. There's also an additional cycle which seems to be peaking every 40 years. All right, and then the next one in Washington, there is an overall increasing trend. Over time in the Washington gross business incomes from 2005 to 2010. And then within each year, there is also a cycle that ends with a peak in the fourth quarter. All right, so like any other writing, you're using complete sentences. You're telling the reader what the numbers are about. Well, in this case, there's not many numbers, but you're trying to explain what the patterns are and what kind of cyclical patterns there are. And the reader should know what the variables are as well. So we've got years, we've got, in the second one, we're Washington gross business incomes. All right, so let's do some calculator stuff. All right, so this is being able to well, let's try to do a scatter plot, huh? So let's say we had the numbers. Okay, so first thing you want to do is you want to put the data in there. So we need X values and Y values. So you go to stat, and then you want to go to edit. Oh, now it's in my eyes. Wow. Can you see that? Okay, it's good enough. All right, let's just move on. Edit. All right, so this, let's say you had a list from previously entering. You can use the arrow keys to go over, and then you hit clear on the list one, and it clears all of that, and then enter. And so now we can do some fresh data on this list. Usually you just do X values in list one and Y values in list two. So let's say these ones are, you can just enter in each of these. So 2, 5, 6, 7, 8, 9. And then I already put these guys in. So 100, 200, 220, 238, 250, 290. All right. And then after you get them in, we would like to go to stat. Oh, let's look around here. Well, let's just look at some stuff here. So there's one variable stats. That can give you your mean, your median, standard deviation, all of that stuff. Oh, okay. So let's go back. Well, okay, it's stat. So you hit stat, and you go to the right. And then you've got one variable stats, two variable stats. Let's just hit enter on the one variable stats. It just naturally, I think it just goes list one. Yeah, list one is the one it pulls up. And then it gives you, the X bar is the mean of the sample. And then we also have a sum. They give the sum. Remember this symbol is the sum of all the X values. Here's the sum squared. So the sum of the squares. This one is the standard deviation, S sub X. And then this one is the standard deviation as well, but that one is for the population. So the sigma is for population, the S is for the sample. So in this case, we'd want to use the sample because it really is a sample. And you can go down, so we've got N as the sample size, got min, Q1, median, Q3, max. So yeah, that's a lot of helpful stuff. Okay, so let's go to StatPlot. So second, and then it's this one right here, StatPlot. So here it gives you which lists you're using. So list one, list two. Let's enter on that, and we want to turn it on. And then see, we've got scatter plots. We've got like a time plot, histogram, all that kind of stuff. And then here you put in your lists, and we have our mark. So let's just try graphing and see if it actually shows up. Oh, I got this one from that old one. So this one, you don't see any numbers. And that's because we don't have the right window. So our Y values were between 100. So let's just go between 90 and 300. And let's make the tick marks be 10 every 10. And then our X values are between 2 and 9. So let's just go between 0 and 10. And there you go. There's the little scatter plot right there. Any questions with that? All right, so there won't be a lot of that, but you may have some online homework questions that want you to look at scatter plots or things like that. You may want to just put them in or something. All right, anything else? Oh yeah, let's just go over it right now. there's this thing called LinReg. That'll be useful for the next chapter. The linear regression is what the LinReg stands for. And it's in the form ax+b. So you hit enter on that. It just naturally takes list 1, list 2. And then it gives you what A is 25. And B is plus 58. Oh, and we would also like an R value with this, I would think. And some of you may be seeing one right now, but to make sure it's turned on, you go second, catalog, and then you go to DiagnosticOn. So go to the D's. DiagnosticOn. Hit enter on that. And then let's go back to the LinReg and see if it gives us. Yeah, there we go. It gives us an R value and R squared. So that's useful. So it's a pretty strong correlation coefficient there, pretty strong relationship. Did everybody find that R value, that DiagnosticOn? Oh, catalog is by 0. So you go second, and then it's right. Oh, you can't see it. It's right here. And then you get a big old list. You can scroll down, or I think you can just hit the D's. Yeah, you can hit the D's and go to DiagnosticOn. Enter on that. And it says done. All right. So I think let's make a time plot in StatCrunch. And then let's start with the next chapter a little bit, just get our little intro there. Probably just be like 10 minutes or something like that. All right. So let's just do some climate change stuff. So time plots, remember they have the points. So they're like scatter plots. So you actually go to scatterplot right here. And then the X variable is always time, or year in this case. The Y variable, let's just do the parts per million of carbon dioxide. And then there's an option for lines, display lines. And that should be good. There we go. It gives a little time plot. You know, honestly, I don't know what is DJIA. Oh, yeah, let's look at global temperature too. So stat or graph, scatterplot, time, and then let's look at the global temperature. And then we have the lines is what we want. Here we go. It's going up and down. So that's the weather. And then here's the climate as the overall trend. All right. All right, so that was just a fun little thing. Let's go back. Any questions with the time plot? All right. So let's start in the next chapter then, without further ado. So here's the last chapter that will be on the test. Sorry for the blinding light. All right, it's linear regression. So we want to be able to model this best fit line, or to do a linear regression, is in other words. So let's make the connection here. So the normal distribution was a model. So that means that these numbers were just helpful for us to find shaded regions and to find these probabilities and all that. But they weren't actually like data points. Same way with linear regression. It's not actually data points. It's a line that just goes through most of the data points. So it models the relationship between two quantitative variables. And then here again, we just have two parameters. We just need to know the y-intercept and the slope. Those are the only two things you need to know to draw a line. And so the parameters specify a particular model. In this case, it's a linear model. And again, models are great when they're flexible, that you can be used in many different situations. Okay. So here we've got a the response variable again is y, so that's the one we would like to predict. And then the explanatory variable is the x. So that's the one that we're gathering the data, and then we would like to predict the y. And so down here, there's a new symbol for predicted values versus observed values. So here we call this y hat, because that's the one that comes from the model. So it's a predicted value. It's not like an actual value, like real life. Like you didn't measure that. You just predicted it. And then this one is the one where you observed, or it's the one that's in the data set, those y's. So maybe I'll just draw it again. Y hat. Kind of a little bigger. There's a little wedge above there. And you pronounce it like that. Y hat. All right. All right, another word here to know is what a residual is. So residual is just the difference between y and y hat. So it's the difference between the observed and the predicted. So how far off are you from the reality there? So this E stands for the residual, and you could think of E stands for error. You know, they both start with the letter E. Okay. All right, so then we actually have an equation for this model. The equation is like you would expect. It's a looks like a linear equation. So there is actually an equation for the normal model, but it's a very complicated equation. So, and it's not very useful for this level just to look at. So with this model, you should be familiar with working with lines with that slope-intercept form. So y equals mx plus b. So things are just in a little bit of a different order. It's a statistics thing. So this one is the y hat. And then the m is like your b one. You see, it's the one that's next to the x variable. And then this guy over here is your b0. So if you're used to y equals mx plus b, you can still think of things like that. You just have to realize that your calculator will give you like a plus bx or some other letters, and you may be shown the b0 plus b1x form as well. So you just have to be able to translate that to a way that makes sense to you. All right. So this b sub 0 is the y-intercept. So that's where it intercepts. Well, yeah, I'll just draw a picture. So the y-intercept is right there. And then the slope is how steep the line is. just a little bit of a review. And the slope represents how much the predicted value of y increases when x increases by 1 unit. So this is something that will be, you need to know how to do. So interpret slope. That's what's going on right there. So you may be asked to do that in a problem. Say, oh, okay, what's the slope mean here? All right, so let's look at this example here. So we've got trees, and then we're wondering how old these trees are. So one way to know how old a tree is by, cutting it down. It's kind of destructive. You just chop it down. You count how many rings are in there. So this is another one of those cyclical patterns. So depending on when it's growing the most, the rings look a little different inside the tree. Or the inside of the tree looks a little different right there. So and it makes the concentric rings right there. And you can count them. So yeah, all right. So here we've got 27 trees of the same species that have been cut down. And then they counted the rings to determine the actual age of the trees. So hopefully we can use this model so that we don't have to cut down every tree in sight to be able to tell how old it is, but we could just measure the diameter of the tree instead and just say, all right, based off this model, this tree is this old. So. All right, so the question is, so can we use a linear model for this? You look at it and you say, okay, well, the points kind of look linear. They're lining up. So yes, you could use a linear model. So it would seem to be appropriate. And then here's the question of why did we put x on the x-axis as opposed to the other way around? Why is diameter on the x-axis? And then the age is on the y-axis. Usually time is always on the x-axis. But in this problem, we're trying to predict the age. So that's why it's on the response variable. So we are predicting tree age. That's why. All right, so let's just look at the next page here. This will be our last page. So we've got the least squares method. Oh, wait, I wanted to draw something, I forgot. So let's get a picture of what the model looks like. It looks like a line. So it looks like, so there's the model. Notice that it doesn't necessarily go through any points, really. It just kind of goes, it's really close there. But then there's also this distance off right there. So this point is different than the prediction. So here we've got a distance off, a little bit off. So remember that E equals y minus y hat, observed minus predicted. So if the observeds are above the line, these are positive residuals. If the predicted are below the line, these are the negative residuals. You can think of them as that. It's the distance of those little lines that I drew right there. Oh, residual, it's the, so think of it as like a little extra. So like a residual of like maybe a drink you're drinking would be whatever's left over on the bottom that you just didn't get to. In this case, the residual is the difference between the actual, so the observed, and the predicted. So like if you had a cup that was 10 ounces, the actual would be 10 ounces, and then the residual would be the difference of the liquid that's still stuck on the sides of the cup that you didn't drink. So it's a very small residual in that case. All right. Any other questions? All right. How are we doing on time? We're doing good on time. All right. So let's see you on Wednesday then. All right.